Hello everyone, welcome back to Coding with Jess. So today we'll be looking at another very common coding question called validate binary search tree. I personally have encountered this question twice in my interviews. In my opinion, it is a great question to test the fundamentals of a binary search tree. The question statement is very simple. You're given a binary tree and you're asked to determine if it is a valid binary search tree. So first, let's take a look at what is a binary search tree. A binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search tree. If you're looking at a tree with its root value 2 and its left child valued 1 and its right child valued 3, is it a binary search tree? It is. Now let's look at another tree with its root value 3 and its left child's value 1 and its right child's value 2. Is this a binary search tree? Apparently no, because the right child needs to be greater than its parent's node's value. So basically for this question, to validate whether it is a BST, we need to check for each node whether the value of each node is in the correct range. So if the node is the right child of a parent node, its value needs to be greater than its parent node. If a node is its left child of a parent node, its value needs to be less than its parent node. So do we only need to check one node's parent's value? That is not true. We also need to check its ancestor's value. Say if we are looking at another node, D, and D is the parent node to A is the right child of D, then the boundary for node B's value needs to be less than A but greater than D, because B is on the right subtree of D, and all the nodes of the right subtree to D needs to have a value that's greater than D. So how do we pass down the lower and upper limits to a node? Well, we could use recursion. In the recursion function, we need to check whether the current node's value is in between its upper and lower limits. If it is not, then we just return false. If it is true, then we keep on going with its left child and its right child, updating their lower and upper limits until we reach the end of the tree. So how do we update the nodes' upper and lower limits? Say if you're looking at a tree like this. The root node's limits are negative infinity and positive infinity. And when we move to its right child, node B, node B's limits will be updated as well. Since node B is the right child of node A, we immediately know that the value of node B is going to be greater than the value of node A. So the value of node A would be the lower limit for node B instead of the negative infinity, which is the lower limit of node A. And the upper limit still stays the same as node A, so it's still going to be infinity. Now let's move on to the left child of B. Since node C is the left child of B, we immediately know that the value of node C is going to be less than the value of node B. So the upper limit of node C is going to be the value of node B. And the lower limit of node C carries from the lower limit of node B, which is the value of node A. Now let's move to the right child of node B. Since node D is the right child of node B, we immediately know that the lower boundary of node D is going to be the value of node B. And the upper boundary of node D carries from its parent node, node B. So it's going to be infinity. Now that we have figured out how to update the lower and upper limits of each node, we should be able to write the recursion. Let's call it the helper method. And for the helper method, we're going to take in a root, which is a node, and the lower bound, and the upper bound. So the first thing that we need to check is whether the root value is in the lower bound and the upper bound. If root is less than or equal to the lower bound, or its value is greater than or equal to the upper bound, it means it is not valid. So we return false. And then we need to check whether it has a left child or not. If root.left, meaning it has a left child, and we recursively call this function with its left child, and we update the lower bound and the upper bound with reference to itself. So since it is its left child, we need to update its upper bound. So we keep the lower bound, and we update the upper bound to root.value. And if it is not, so meaning the recursive function eventually returns false, then we return false here, meaning it is still not a valid BST. Similarly, we do it for its right child, pass in its right child, and this time we're going to update its lower bound because it's its right child. So for the lower bound, it's going to be the value of the root, and then we keep the upper bound. And if this eventually returns false, we'll return false here because it's not valid. And if we haven't returned false throughout the whole tree, we return true. So that is what the recursion method looks like. Now let's complete the whole code for this question. As usual, the first thing that we need to check is whether the given root is valid. If not root, we return true, because if it's an empty tree, then it is a valid BST. And then we could just return calling the helper method with its root. And for the lower bound, since it's its root, we could just pass in the negative infinity. And for its upper bound, similarly. So let's take a look at the runtime and the space complexity for this question. For the runtime, since we need to go through every single node to check whether it is inbound for its lower bound and its upper bound, so the runtime would be big O of n being the number of nodes in this tree. And for the space complexity, since we're calling the function recursively, so say if you're looking at the worst case scenario when your tree is all linked up, so basically it looks like a linked list, then we'll have n elements in our stack. So the worst case scenario for our space complexity would also be big O of n being the number of nodes. Alright, so that's it for today's video. I hope you have enjoyed it. Please give this video a thumb up if you found it helpful, and feel free to leave any comments below, and I'll see you in the next time. Bye!